All right, hello everybody, welcome back. Today we're going to talk about standing normal shocks. We talked in our last lecture about the converging diverging nozzle system, and when we were talking about operation of that nozzle, we talked about the specific operating conditions called like the first and third critical, and how in between those operating conditions, you would have shocks inside the diverging section of the nozzle, and these shocks are in fact standing normal shocks. And so what we're going to do today is start talking about those and learning about the physics surrounding them so that we can continue our analysis of these types of nozzle systems in a quantitative way. Okay, so before we go into that sort of detailed mathematical analysis though, let's talk a little bit about shocks in general and take some time to demystify them and give you an idea of what's physically occurring, okay? So, most people, when they get into this course, have not seen or studied shocks in their coursework before. So they don't have a good idea of what's happening in their mind at a shock. So the first question simply becomes, when do shocks occur? And the answer to that question is simply when flow speeds exceed the speed of sound in a medium A, and that's not that's a necessary but not sufficient condition to cause a shock. You can still have greater than Mach 1 flow without a shock occurring. But this is sort of the shocks must have this be the case, and that's a critical fact for understanding why shocks occur. So because the constituents of the flow are traveling faster than information can travel through the medium, so the constituents of the flow, meaning the little molecules that make up the macroscopic flow, they're actually traveling faster than information can travel through the medium. The molecules basically can pile up and form a tiny region of small dissipation. Of strong dissipation. So molecules pile up, form small, strong dissipation region. And I'll explain what I mean by this. Let's start with the standard equations which describe fluid flow in one dimension. So we're going to look at sort of the normal one-dimensional Navier-Stokes equation. Okay, and I'll just write it here. Normally I would ask students to tell me what the terms are, so keep that in mind. If you can't write these down on your own, you should study and familiarize yourself with Navier-Stokes. So this is Navier-Stokes in one direction, specifically the x direction, assuming that the problem is 1D. So you have essentially the material derivative on the left-hand side. On the right-hand side, you have the pressure gradients, which typically drives the flow, and then you also have this dissipative term, which has to do with viscosity. Okay, so this term is often called the viscous dissipation term. Okay, and it's made up of irreversible processes, right? Like friction. Think of it as like friction. Okay. In general, in any sort of partial differential equation, if you see let's say a Laplacian of something, like a second derivative in space, it's causing sharper structures to spread out over time. If that component of the equation is also included with some sort of time derivative, you're going to have some sort of spreading out. And the constant in front of that tells you how fast these things spread out and dissipate. In this case, it would be the viscosity. And so a shock, they have a width of a few mean free paths, okay? So, and I'll explain what that means. Shocks have a width of a few, and the way you write mean free path is using this Greek letter lambda sub fp, okay, which is about 10 to the minus 8 meters, say, for air. So what that means is that actually, here I'll cross that in a second. So let me explain what mean free path is for a moment. So mean free path is the average distance that one of the molecules travels before it has a collision with another molecule. Okay, so it's the mean distance it travels that it travels freely before interacting with another molecule. So it's normally very, very small, and you can imagine that if we're looking at these flows as a continuum medium, the mean free path sort of is like the minimum resolution. If we're looking at resolutions that are small enough where they're on the order of several mean free paths, that means that a continuum description like Navier-Stokes doesn't really apply anymore, because now we're actually looking at a situation where we can see individual molecules flying around and not a smoothly varying medium. So shocks in general are very, very small, and in that region, in that tiny shock region, I'll draw a shock here. Typically in this class, shocks are just going to be drawn with a vertical jagged line like that, right? Near that shock, or within the shock, right, within that small region defined by the shock, the term in the Navier-Stokes equation associated with dissipation is very large. So mu times d squared u dx squared is really big, because a shock represents a change in properties over a really small region. In this case, only a few mean free path. So it's like essentially almost like a sharp line, and that's what you've seen in those pictures of shocks that you may have seen before. And so the properties are changing really, really quickly, and therefore the second derivative is also very, very large. So that's where I started here. I was saying the shocks have that really small width, so the second derivative with respect to x of ux is really, really large. Okay, and so that's how we know that this dissipation region has a very large dissipation, whereas outside of the shock region, it looks like Euler flow, where mu d squared u dx squared is small. Euler being ideal flow. That's what the Euler equation describes. Okay, or inviscid flow. Okay, so outside the shock, you still have your continuum normally ideal equations that you're used to, but inside that shock, you have strong dissipation. And the idea is your sort of flow chart of events is you have the pile up, which leads to a small region with big gradients, which leads to irreversible processes that converge, I'll just say that results in conversion of flow, the energy of the flow, to heat, which we'll just call like losses. Okay, and then this reduces flow velocity to subsonic levels. Okay, so downstream of a shock, after a shock occurs, the flow velocity is always less than Mach equal 1. So it's an abrupt drop from supersonic conditions to subsonic conditions. Okay, so that's what's going on inside of a shock. Hopefully that gives you a bit of an intuitive picture in your head of what's going on there. So now let's start to actually derive the relations related to standard normal shocks. Okay, so I'm going to draw a diagram here, like a section cut of a varying area duct. And then let's say that there's a standing normal shock in the center, and we'll go ahead and draw a tight-fitting control volume around it. So here we have A2 on the right side, A1 on the left side for the cross-sectional area in state 1 and state 2 on the left and right. The overall width of this is some sort of infinitesimal dx, very small width, so it's tight-fitting, like I said. The velocity exiting the control volume is V2, and the velocity entering the control volume is V1. And then we also have P1 entering the control volume and P2 exiting for the pressure. Okay, so first, since, like I said, we're going to assume that dx is infinitesimal. You may have guessed this as you thought through this while I was drawing, but that's basically going to imply that A1 is approximately equal to A2. They're about the same area, right? And then it also tells us that, and we said this, we mentioned this before, I think when we were looking at deriving the speed of sound, that this implies that we can ignore the surface friction effects, because the surface area on the top and bottom of the control volume is really small, since the control volume is tight-fitting around the shock. So therefore, any surface friction would be over a very small area and negligible. Okay, we're also going to assume that this is a steady-state problem, that this is 1D as always, and that there is no heat transfer, no work done, and that the potential changes are all negligible. Okay, so all of our sort of standard simplifying assumptions. So then we want to go ahead and look at the conservation of momentum, mass, and energy. But usually we start with mass, just because it usually leads to the simplest relations. So for continuity, we know that for a 1D steady system, that m dot 1 is equal to m dot 2. And that's just going to imply that rho 1 v1 is equal to rho 2 v2, because a1 is equal to a2. Okay, so we'll just call that equation 1. Then we'll take a look at conservation of energy. In that case, we have the total or stagnation enthalpy at state 1 plus any added heat is equal to the stagnation enthalpy at state 2 plus any work done. Okay, we mentioned that these are both 0. So this is telling us that the total stagnation enthalpy is constant, but also broken out into the stagnation enthalpy and the velocities. We can write that as h1 plus v1 squared over 2 is equal to h2 plus v2 squared over 2. Okay, and that's, we'll call that equation 2. And then, of course, we want to look at conservation of momentum, where we have the sum of all the forces in the x direction is equal to m dot times v out in the x direction minus v in the x direction. Right? That's just Reynolds transport theorem with those values plugged in. And that will tell us that we have P1 minus P2 being equal to rho 2 V2 squared minus rho 1 V1 squared, right? So that's noting that all the forces are just the pressure forces on the left and right. Those forces would be the pressure multiplied by the area. And then on the right-hand side, we have the m dot, which is just rho VA. And so we can drop out the areas cancel out. Okay, and then also noting that the mass flow rate can be written in terms of V1 or V2. It's totally fine. Okay, and so we can rearrange this and write P1 plus rho 1 V1 squared is equal to P2 plus rho 2 V2 squared. And then we'll call this equation 3. So those are our 3 equations that we'll work with. So let's take, so first, let's use, so take the ideal gas equation of state, that's what EOS stands for, P equals rho RT, as well as our velocity written in terms of the Mach number, which would be m times gamma RT, the square root of gamma RT rather. Okay, then we'll rewrite equation 1 as P1M1 over the square root of T1 is equal to P2 M2 over the square root of T2. Okay, there's one more thing that we're assuming here, which is that gamma is constant. Okay, so also assuming gamma constant. Okay, in that step of this derivation. Okay, so we know from 2 that H1T is equal to H2T. We'll assume a perfect gas. So T1T is also equal to T2T. Okay, and then we can just write down our equation for the stagnation temperature in terms of the static temperature on the left and right, which so essentially we can write that T1 times 1 plus gamma minus 1 over 2 M1 squared is equal to T2 times 1 plus gamma minus 1 over 2 M2 squared. Okay, we're going to actually label this equation and call it equation 5. And I forgot to label this guy as equation 4, sorry. So equation 4 and 5. Okay. So we're also going to make the same substitutions in equation 3 as we did in equation 1. So that is the ideal gas equation of state in V in terms of the Mach number. And that tells us that we have P1 plus quantity P1 over RT times M1 squared gamma RT1 plus, is equal to P2 plus P2 over RT2 times M squared 2 gamma RT2. And you can see that the RTs cancel on both sides here. This is be an RT1 down there. And we end up with this equation where we have P1 times 1 plus gamma N1 squared is equal to P2 times 1 plus gamma M2 squared. Okay, and we'll call this equation 6. So if we know the working gas and the upstream conditions, so we're going to assume that. So assume we know the working gas and upstream conditions. Which would be sort of gamma, P1, T1, and the upstream Mach number M1. These are all fixed. So then we'll use equations 4, 5, and 6 to solve for the downstream conditions. Okay, so let's start with 4. That's where we have P1 M1 over P2 M2 is equal to the square root of the ratios of the static pressures, or sorry, static temperatures. And then we can rewrite that using relationship 6 or equation 6 as M1 times quantity 1 plus gamma M2 squared over M2 times quantity 1 plus gamma M1 squared is equal to the square root of 1 plus gamma minus 1 over 2 M2 squared over 1 plus gamma minus 1 over 2 M1 squared. Okay? So before we proceed, in fact, we're going to actually skip some steps. But for a moment here, let's make some observations about this guy. So the first observation is that there's a trivial solution here where just M1 is equal to M2. And in that case, you have no shock, right? So that's not an interesting solution, but we should point it out. M1 equals M2. So in that case, this we would end up with a equation that says 1 equals 1, which is true, but not very useful. The other thing that's very important is that M2 only depends on M1 and gamma. So your working gas parameter gamma, as well as your upstream Mach number. So it doesn't matter what the temperature or pressure is upstream, it just matters, all that matters is the upstream Mach number, and that determines what M2 is. Okay, so at this point, going from this equation, we're going to skip some algebra. That's not very illuminating. And we're going to write that M2 squared is equal to M1 squared plus 2 divided by gamma minus 1, all divided by 2 gamma M1 squared over gamma minus 1 minus 1. Okay? So we'll go ahead and box this guy. That's a nice equation to know. And then we can also find P2 and T2 after knowing what M2 is using equations 5 and 6. Okay, so now we have all our downstream conditions, all basically determined by the upstream Mach number. All right, and this was already mentioned, and you'll actually, I think you'll show this in your homework. Since M1 is greater than 1, strictly greater than 1, for a shock to occur, M2 is less than 1 always. Okay, and you can show that mathematically using this equation here. So let's before we proceed, let's draw what's happening in a shock on a TS diagram. So let's say we have some state 1 here, and then we have a state 2 here, and then M1 is sort of represented by this horizontal line here. This is M equal 1, I should say. And then the shock process is this sort of entropy producing process that goes from state 1 to state 2. Okay, and you have different pressures. So the pressures are the sort of level set lines for pressures are kind of tilted like this. So we give you P1 and then P2. And then you can also go up in this direction to get your stagnation pressure. or your stagnation state to T, and you can see that's P to T, and then let's go up here, this direction, to 1T. So these are both, Mach equals 0 states, but they have different pressures. So you can see that the stagnation pressure actually drops across a shock. Okay, pressure is increasing this direction. Okay, and these sort of vertical distances here between the stagnation state and the static state are V1 squared, or the actual thermodynamic state, or V1 squared over 2Cp. Okay, and that's just because our stagnation temperature does not change between the two. So stagnation temperature not changing across a shock, but stagnation pressure is most certainly is changing. Okay, that's a very important distinction and something that you'll know you'll use a lot. So this is our shock process, and I'll put process in quotations here because it's definitely like not a quasi-static process that you could draw nicely on a thermodynamic diagram. Okay, hopefully that's not too messy of a diagram. It didn't look that nice, but hopefully it's useful. Okay, so let's now talk about the normal shock tables. And this is a lot like the isentropic relations that we talked about. Yeah. Oh yeah, it was at the beginning of the last lecture. In general, when we solve for M2, we showed that it was just a function of M1 and gamma, and we can use that to sub into the relations for T1 and T2, etc. All of our working equations. So we have working equations for P2 over P1, T2 over T1, etc. We can sub our expression for M2 downstream of a shock into these. And what you end up with is, T2 over T1 being some function of just M1 and gamma, and the P2 over P1 being some other function of M1 and gamma. And then also that PT2 over PT1 is some other function of M1 and gamma. Okay. And like I said, it's very important that you note that the stagnation pressure changes across a shock because you have losses occurring across the shock. So, we showed that PT2 over PT1 is also essentially equal to e to the minus delta s over r. I might have this sign, I'll just put a plus or minus here in case I have that sign wrong. Let's see, if the entropy, I think it's a negative for if PT2 is on the top, right? Because we want the stagnation pressure to drop across the shock. But so you have this case. So because there's some irreversible losses occurring across the shock, we do have a change in the stagnation pressure across the shock, as opposed to uh, uh, stagnation temperature, which stays the same. And we can actually use this relationship PT2 over PT1 equal to e to the minus delta S, delta S over R. This allows you to get the change in entropy across a shock as a function of N1 and gamma, because the stagnation pressure drop across the shock is a function of N1 and gamma. Okay, and so all of these are tabulated in Appendix H of Zucker and Biblar's. Okay, so cool. Let's talk about an example. Let's do an example here. So let's assume that we have air as a perfect gas. So that just tells us the gamma is 1.4 and constant. And then we have M1 is equal to 2.0. P1 is equal to 20 psi absolute. T1 is equal to 400 degrees Rankine. And then the question is to determine the conditions after a normal shock and the entropy change delta S. Okay, so the first thing that we want to do is we want to figure out what the stagnation pressure is upstream of the shock. So we can just use the equation if we like, but you can also use the isentropic tables for this. So PT1 over P1 will be in the isentropic tables, and it gives you 1 over 0.1278. Okay, for a Mach number equal to 2. And this tells us that PT1 is 156.5 psi A absolute. Okay, and then from the table, for M1 equal 2, the downstream Mach number M2 is equal to 0.57735. Okay, and then we would know that P2 over P1 is equal to 4.5. This is all just reading off the table values. T2 over T1 is equal to 1.687. And PT2 over PT1 is equal to 0.72087. Okay, and then we just found what PT1 is in the previous point. So then knowing what PT2 over PT1 is, we know that delta S is going to be equal to R times the natural log of PT1 over PT2, which turns out to be 0.0224, and using our correct units here, that would be British thermal units per pound mass, degree Rankine. That would be your imperial units for entropy. Okay, so it's really a big, there will be more complicated problems, of course, but a big part of this is simply reading off values from tables according to what your upstream Mach number is. Okay, so that's an example, and you'll do all sorts of different problems that are kind of that nature. We're going and looking up table values. So then the next section here is shocks in nozzles. So I mentioned that, we have this, that the operating condition of a nozzle, and we talked about this last lecture, is determined by the operating pressure ratio. That is the pressure ratio between your receiver, the back end of your nozzle, and your upstream stagnation pressure. Okay. So let's draw a converging diverging nozzle here. Hopefully I can. That looks pretty good. And then we'll do a vertical line down through the throat here. And we're also going to draw a pressure variation diagram right underneath it. Same as we drew before, where this is the throat location. This is the pressure. And let's go ahead and draw. And in fact, let's draw it as, let's plot specifically the local pressure divided by the upstream or incoming stagnation pressure, okay, which is the pressure ratio that we care about, right? Let's go ahead and draw the first and third critical operating conditions that we had last time. So it goes, we know it goes down like this, and then the third critical continues down like that, and then the first critical would go up this way. So that's the first critical. And this is the third critical. Okay, and then we know that this is sort of all Venturi stuff up here. Okay, so these are sort of important facts to know right here. This will help you in homework and also in exams. We want to note that the first and third critical points or operating conditions have the following characteristics. So one is their isentropic flow throughout. In other words, there are no shocks present. We do, both cases have m equals 1 at the throat. And then the pressure at the exit is equal to the pressure at the receiver, or the sort of atmospheric pressure. Okay. So in other words, the pressure once you get to the end of the nozzle, as you've gone through this operating condition, perfectly matches up with the environmental pressure at the end of the nozzle. Okay, and that you might be kind of confused of how that's even possible for it to not be equal, but we'll sort of discuss this in further detail as we go along. If you have subsonic flow, that is like up in the Venturi regime, the pressure at the exit must be equal to P at ATM, right? If you have subsonic flow at the exit period, you're going to have the exit pressure be equal to the atmospheric pressure, and that must be true because you have subsonic flow. So you can't have any discontinuities in properties, right? For that, you would need supersonic flow with shocks. So this must be true. And then what you do is, if you start at the first critical and you decrease the exit pressure of the receiver, no isentropic flow will allow for PE to be equal to the atmospheric pressure. So a non-isentropic process, in this case a normal shock, will make flow downstream of the shock subsonic. So that way you can ensure that PE is equal to P atmospheric, okay? So what do I mean by that? So let's say that we place our exit pressure or our atmospheric pressure up here, right? This is some in-between pressure, so we'll just do P. I won't even label it. So let's say it's right there, right? What would have to happen is these are the only two isentropic operating conditions that get you to the exit. So what actually has to happen is you have to proceed along the third critical line up to a certain point, and then a shock will occur, okay, bringing you to another isentrope that allows you to continue forward and meet that pressure boundary condition at the exit of the nozzle, okay? So the shock that's occurring along this particular path is occurring so that you have so that you can meet that pressure boundary condition. So if no isentropic flow allows for P E equal to P atmosphere, a shock forms in the nozzle, specifically in the diverging section. And it forms in whatever position is necessary to give you P equals P atmospheric. Okay? And then, if you continue to lower that back pressure, the back pressure that gives you a shock right at the exit, right here, that is your second critical operating condition. Okay? So this pressure right here is called the second critical. And that is defined as the pressure operating condition that places the shock right at the exit plane. Okay? And this sort of, this bit here is what we would refer to as overexpansion. So in other words, you've written down inside the nozzle, when you say overexpanded, you mean the nozzle has brought the flow down to a pressure that's too low to meet the back pressure, and then it has to jump up through a shock process. So that's an overexpanded nozzle. And then that's why if your back pressure is below the third critical, anything down there is referred to as under expansion. So this is under expansion, but we'll talk more about these terms over and under expansion later. Okay. So let's actually find the second critical point. So let's do a simple little converging, diverging nozzle picture here. Let's say we have state 1, state 2 will be at the throat, state 3 will be just upstream of the shock that's occurring right at the exit, and then state 4 will be our atmospheric back pressure state, okay? So we're going to work with the same converging, diverging nozzle from the last lecture, which is we had PT1 was equal to 100 psi A. T1 was 600 degrees Rankine. We had A3 over A2. Over A2 was 2.494. Is that right? Did we have that? Yeah, we did. Okay. And then from there, we determined that the third critical operating condition, just from looking at the tables pretty much, was that P3 over PT3 is equal to 0.06426, and M3 was equal to 2.44. Now, why are we finding the third critical operating condition if we're looking for the second critical? Well, for the second critical condition, everything all the way up to the exit is exactly the same as the third critical. So, so basically, anytime that you're looking for the third critical pressure ratio, you need to find what the upstream Mach number is of the shock at the exit, and that upstream Mach number is going to be essentially what the Mach number would be at the exit if you were on the third critical, right? Or if you were at the third critical operating condition. So that M3 becomes your upstream Mach number for the shock at the exit. Excuse me. So for the normal shock tables, which again I think is Appendix H of Zucker and Biblar's, for M3 equals 2.44, we have that the downstream Mach number, M4, is going to be equal to 0.5189, and P4 over P3 is equal to 6.779. Okay, so that's just reading off the table. We get what M4 is, and we know that P4 over P3 is. So then what's our operating pressure ratio, right? The pressure, the P4 is what the back pressure is, right? That's the receiver pressure. So operating pressure ratio becomes P, it would be P atmospheric, P receiver over PT1. That's going to be P4 over PT1, which we can expand out, is P4 over P3. So we just read that off the table, multiplied by P3 over PT3. We got that from our third critical calculation. We read that off that table for A over A star being equal to 2.494. I should actually write this down. We made this note. When we did this before, but I should note that this is from the isentropic table where A over A star is equal to A3 over A2. Okay. Okay, and so then we have P3 over PT3, and then we have PT3 over PT1, right? That is just 1 because there are no losses between state 1 and 3. It's all isentropic between there, so there's no drops in stagnation pressure. So that goes to 1, and then we have the two table values, and if we put those together, we get 0.436. Okay, so for this area ratio, the operating pressure ratio would be this, and our actual atmospheric pressure or back pressure would be 43.6 psi A to operate at the second critical. Okay, so now let's kind of proceed to talk about this. So the first critical, in this case, and again, this is actually reading off of just getting the subsonic root from the area ratio. So you go to the when you look for the value of the area ratio in the table, you're going to get a supersonic Mach number. That corresponds to the third critical. And then further up on the table, you'll get another Mach number solution. Will be subsonic, and that will be the first critical. So we can read this off the table as well. And the first critical in this case gives us P atmospheric over PT1 is equal to 0.9607. Okay, so any pressure ratio where we have that's between 0.436 P atmospheric over PT1 and 0.9607. If the pressure ratio is between the first and second critical, we're going to have a shock in the nozzle. Okay, So looking back at this diagram here, the second critical, the shock has moved all the way to the edge of the nozzle. And then the first critical is when it goes up to Mach 1, but then it goes back to subsonic and goes isotropic that way. Okay, so all of the other potential back pressures between those was going to result in the flow traveling down the isentropic branch to a certain point and then having a shock and having to go over and meet it. Okay? So you're going to have some sort of shock in the nozzle if you're in that regime. Let's go ahead and suppose that P ATM, or P receiver, divided by PT1 is equal to 0.6. And then the question becomes, where is the shock? I'll go ahead and kind of highlight that in purple so we know that we're doing a little bit of an example here. So in this case, our situation looks like this, right? We have a converging, diverging nozzle. We have state 1, the upstream condition. We have stage 2 at the throat. And then we have a shock somewhere in the interior of the nozzle. We don't know exactly where it is yet. We have 3 and 4, upstream and downstream of that shock. And then we also have the exit, which we'll label state 5. Okay, so first off, we know A5 over A2 is equal to 2.494. Okay, that doesn't change. And we also know that P5, the exit pressure, divided by PT1 is equal to 0.6, right? What else do we know? Well, we know that M2 is equal to 1 because the flow is choked, right? So if we have any sort of supersonic flow beyond the throat, we know that the flow must be choked at the plane of minimum area. Okay, we talked about why that is in previous lectures. So if M2 is equal to 1, that means that A2 is equal to A2 is equal to A1 star. So in other words, the area at area 2 is equal to the sonic reference state area for everything upstream of the shock. Okay? So what we can do is we can use this fact. So we know what A5 over A2 is. And we can use this fact along with that closure piece that we talked about before, right? To calculate what the sonic reference area should be downstream of the shock. Right, so using these two facts together, we have A5 over A2 is equal to, or times P5 over PT1 is equal to A5 over A1 star times P5 over PT1. Okay, we just replaced those two pieces there, or just replace the A2 with A1 star. Okay, and the reason why we do this is because we know what this is, and we know what this is, right? So we this is just some sort of known value. Okay, so remember, for a process where there's no heat addition or work being done, and for a perfect gas, we showed that A1 star times PT1 is going to be equal to A5 star times PT5, right? So we can write this as if we write A5 times P5 over A1 star times PT1, we can replace the denominator A1 star with A1 star PT1 with A5 star PT5, okay? And so then you have A5 P5 over, A5 star PT5. And now this is just a function of the Mach number at 0.5 and gamma, because P5 over PT5 is just a function of Mach number, and so is A5 over A5 star, right? So A5 P5 over A1 star PT1, that is just some known value, so some like constant C, right? And we can show that this constant C is also equal to A5 P5 over A5 star PT5 star PT5. And then we can use the tables to relate that back to the Mach number at 5. Okay, and that tells us that the Mach number at 5 is approximately equal to 0.38. Okay, and you don't even need to use the tables. You can solve that numerically using the actual relationships. Okay, in fact, for this case, since you're simultaneously using two different columns of the table, it would probably be easier to use the two different relationships and solve for them. Okay, so now we got the Mach number at the exit. Why are we doing this? Well, we need to find out what the stagnation pressure drop is across the shock. So to locate the shock, we need to find PT5 over PT1. And to do that, we have PT5 over P5 times P5 over PT1. This is given in the problem statement. We know that's 0.6. And then PT5 over P5 comes from the table. Now that we know what M5 is, or the Mach number at the exit. And that tells us that this is 0.664. Okay, so now we have the stagnation pressure drop across the shock. So, looking at that, and this is because, no losses before or after shock. And that's why, PT1 is actually equal to PT3 and PT5 is actually equal to PT4. That's why I called the stagnation pressure ratio PT5 over PT1 the stagnation pressure drop across the shock, because this ratio here is exactly PT4 over PT3, and it's equal to 0.664. Okay? And we can actually then just, now you look at the shock tables, right? And the shock tables tells you what the upstream Mach number would be, which would be M3, approximately equal to 2.12 from shock tables. Okay, so now we found the Mach number that's upstream of the shock. And then, last step, find A3 over A3 star. Okay, A3 star is A2, right? Because upstream of the shock, between states 3 and 2, there are no losses occurring. So the sonic reference state is the same between those two. So this is equal to A3 over A2. And A3 over A3 star just depends on what M3 is. And it turns out in this case to be 1.869. Okay, and so if we know what the area ratio is between the point where the shock occurs at point 3 and the throat, then we can use that area ratio along with our known nozzle geometry to locate the shock. Okay, so that's a little bit of a more involved example and process there. But I mean, if you can work through this and understand everything that's going on here, then you'll be in pretty good shape for a lot of the normal shock analysis questions. and especially it'll lay a pretty good groundwork for our subsequent work on propulsion systems, where you're going to be hopping through really complicated systems that have more going on than just normal shocks. More, heat addition and compression and other types of processes that can complicate things. So yeah, hopefully this was a interesting introduction to normal shocks. And in the next lecture, we're gonna go ahead and proceed. And yeah, I hope to see you there. Have a great day. And yeah, feel free to reach out with any questions. Otherwise, see you next time. Have a good one.